what do we intend to discuss today? This, people, is my agenda. Now, where joins actually happen. Now, we've all been writing SQL for years, but I just want to drill down quite close to where the join occurs in the execution cycle of a SQL statement. Performance of your SQL queries is always a matter of vital importance, and by all means, putting questions about performance and tuning joins, tuning statements, we're going to pleased to deal with them if we have time. But the main thrust of our topic today is not meant to be performance tuning. It's meant to be a run through not so much syntax, but what you can achieve, what the various join techniques actually are. But performance, try us, and if we've got the time, we can expand on that as well. But in principle, I'll just be giving a very brief summary of the performance impacts. I'm going to go on to talk about the join syntax, ANSI syntax, as against what people normally call Oracle native syntax. And this is a debate that's been going on for years. Which syntax is better, if either is better, which is most appropriate. And different people have very different views on this. And I'm not going to say that I'm always right. I'm not going to say that other people are always wrong, but I'm going to say it's open to debate. I'll give you my opinions, and other opinions from those of you who may be far more experienced developers than me, I'll be only too pleased to take. Then we'll move on to the types of join, the various types of join we've actually got. And I don't mean hash join, nested loop join, sort merge join. I mean joins in terms of ANSI syntax. And I'll be doing a few demonstrations there, which I hope will work okay, and maybe introduce a few sort of possible bugs and issues that can arise. Throughout this will be the concept of the equivalent SQLs is critical. Equivalent SQLs. What's an equivalent SQL? It's two or more SQL statements that are guaranteed to deliver the same result, even though the syntax may be completely different. We can't avoid the concept of equivalent SQLs. They are vital for tuning. Very often, SQLs that are syntactically very different. Well, the cost-based optimizer should recognize that they are equivalent in terms of result set and rewrite them to the same structure. Can't always do that, but certainly the most obvious example of that is ANSI syntax as against Oracle native syntax. The difference is there, and the optimizer is pretty good at matching those, but it can't do that with some of the more complex join structures. So that's what I want to cover. Beginning with the SQL execution cycle. Now, I'm sure that many of you will know this backwards already, but I just want to make sure that we are, as it were, all on the same page of the manual. Beginning with terminology. I am going to try to be precise in my terminology, and I advise everybody to be as precise as possible in your use of words for this. It's not being pointlessly pedantic. It really isn't. Using the correct terminology can be very important to avoid confusion, to avoid wasting time. Take this item here. You select rows and you project columns. A mistake there can waste so much time. And the number of times a problem has been presented as, I'm trying to select something or other. And you spend hours trying to sort it. He's trying to select something and it isn't working. And it turns out that what he actually meant was, I'm trying to project something or other. And always remember, you select rows and you project columns. It's not being pointlessly pedantic. It's important. To take a trivial example, a simple query such as this: select dname from dept. Right, working in the Scott demonstration schema. I am not selecting dname. I am selecting dept, and I am projecting dname. So please bear with me on that. It's not being needlessly pedantic. It's important terminology. You select rows and project columns. Now, that brings one on to the sequence of execution of the various steps in a statement. The typical sequence of events, this isn't necessarily correct for all queries. There can be iterations, things can be done in different orders. As queries get more complex, you may be looping through these things. But for a typical, simple query, this is the order in which Oracle is going to perform the various steps that a query might require. First, the rows are selected. That's the first point. Oracle or your session server process will go to the table and find the rows you want. You select the rows. We're talking about joins today, so we assume there are at least two tables involved. Therefore, Oracle will then go to a second table and select rows from there. Remember, Oracle can join only two row sources at once. So if your query is addressing 20 tables, it will choose two of them and join them to produce a result set. Then we'll go to a third table and join to that to produce the result set. That will be joined to a fourth table. So you begin by selecting the rows from one table. And if there's a join involved, you then have to get the rows from the other table and join them. Right. So when you join them, you get a single result set. So our first two result sets from two tables are joined into one result set. And maybe there are more tables to join in as well. Having done all that, we perform the aggregations. That's your groupings. Your groupings, whatever they might be doing, the groupings, the roll-ups, distinct, remember that's always an aggregation, max, min, count. The aggregations occur next. Next step, assuming it's a simple query, column projection. So the column projection occurs quite late, and that's where we might be doing things like various formatting functions. And maybe you're using toChar on date columns, perhaps, formatting numbers. Various column projections. If you've got those SQL structures where you're projecting scalar subqueries, well, Oracle might not have been able to merge that into the earlier steps. It might have to run them at that final stage of projecting the columns. So projecting the columns is preparing the result set, how it's going to be returned to the user. And the very last step is the order by clause. That's the very last step after the column projection has been completed. This, by the way, this ordering explains perhaps one of those things that many people find a bit confusing. Why is it that you can do something like, say, select, what might we have? Deptno sal, Deptno, say sum sal from emp, group by Deptno, order by Deptno. We can do that. Or we can do this, order by 1. What we cannot do is group by 1. That's impossible. And this makes it clear. It's because using this, the numeric thing, I'm talking about the order in which the columns are projected. And because the aggregation occurs before the projection, that ain't going to work. Whereas the order by occurs after the projection, so that does. So that's your typical sequence of events. Though, of course, there are many variations. And today, I want to talk about the join step. Okay, so far?
Hey, John.
Yes.
Couple questions came in. So first one is person saying they usually think of the SQL execution cycle as being parse, bind, execute, fetch. Is this something different?
Oh, nice question. Yes, it is. The parse, bind, execute, fetch cycle is the complete cycle from the end user issuing the SQL statement. The statement has to be parsed, meaning Oracle works out what does it mean and how to run it. Any bind variables have to be expanded. Then execute if it's a DML statement, or fetch if it's a select statement. Parse, bind, execute, fetch. What we've got here is the fetch phase. This is breaking down the fetch phase into the individual stages of it. So this is kind of an expansion of parse, bind, execute, fetch. What actually happens when you're running the prepared statement.
Okay, and then one more. Where does all this work happen? Which processes and which memory structures?
Okay, this all happens on the server side. So your client-side process or middle-tier process, if it's a web application, generates a SQL statement, sends it to the server, to the database server, where the sessions server process can run the statement, going through the parse, bind, execute, fetch cycle, and this is that fetch part of it. It's all happening on the server side, and it's all done by your session server process. So what does it mean? Well, typically, your server process during the select section, the select phase, will be reading blocks from disk into database buffer cache, into the instance memory, and that's block IO from disk into database buffer cache, unless the stuff is cached already, of course. Then the selected rows, because the blocks might contain many rows you don't want. The selected rows then get transferred into the session server process's PGA, the program global area for that session, the private memory. And that's where the work is done. So it's your session server process on the database server working away in its PGA. That's where this happens. There are, of course, variations there. In some circumstances, you might bypass the buffer cache, and the blocks might be read directly from data file into PGA. If it's Exadata, there's more variations with Exadata. The row selection can be pushed down to the storage cells, so that we don't actually have to do filtering in server-side memory. It can be done by the disk structure. But basically, this is going to happen in memory on the server side. And it's only the final result set that gets back to the client.
Okay, thanks, John.
Right. I did say that we aren't going to spend too much time talking about performance, but I know that by popular request, we always have to include performance issues. So again, just as a reminder of what's going on, we've covered this in other webinars that we've done over recent years. Performance issues of running SQL statements. Oracle will be doing its best to merge views and subqueries. It takes the query you've issued, which might have views in it, it might have subqueries in it, all sorts of things, scalar subqueries, whatever. You might even be projecting subqueries. Oracle will do its best to merge all these structures into one, and that gives it the most options for things like join order and the rest. Then, having done all the merging it can, it will look at the row sources, typically tables, and determine the order in which to join them, because Oracle can join only 2 row sources at once. So if you've got 20 tables, in principle, it has a choice of 20 for the first table to address, then a choice of 19 for the second table, then a choice of 18 for the third table, and so on. So we're talking 20 factorial possibilities here for the join order. It has to work out what order to hit the tables in. It may well involve caching data sets in PGA as it does it.
John,
yes.
Could I ask a question here? Does the developer have to know or have to choose a join order? Or is that completely something that's completely done by the CPO?
In an ideal world, it's completely done by the CPO. And developers, however, can influence this if they wish. It's always a bit of a sore point. The CPO is probably the most complex software artifacts with which you will ever interact. It's more intelligent than all of us put together, but it ain't perfect. And there are times when the CBO makes a mistake in that the join order it chooses is not optimal. If we are aware that that's happening, then there are techniques the developer can use to force a join order. But the approach I would always take, Gary, is trust Uncle Oracle unless you know he's getting it wrong. And if he is getting it wrong, blame your DBA. And if the DBA still can't fix it, then it's down to the developer to fix it himself. But that's the order. Trust Oracle, trust your DBA, and if they both failed, then I'm afraid, Gary, it's down to you. Okay.
Okay, thank you, John.
Now, having worked out the join order, it will then move on to the join methods and the access methods. And again, there's quite a lot of tuning one can muck about with here in terms of join order is certainly the most important decision. If you get your join order wrong, you've no chance. But then we move on to join method and access method. Overall, though, trust the optimizer and we should be okay. All right. Now, in that case, if that's okay, let us proceed.
John, can you hold on 1 minute? A couple more came in. I'm sorry. I had muted myself.
Whoops, sorry. Whoops, just a moment. Get my slides right.
So, what will make view merging impossible?
There are several structures, and this is where we can blame the programmers most definitely. View merging is very important because if views and subqueries can be merged, it gives Oracle it gives the optimizer the most possible choices for join order. But some structures will stop views being mergeable. Typically, it's the syntax of the view. If it's got any sort of aggregation, if there's a distinct in there even, then the views won't be merged. Make sure your views and subqueries do not include aggregations. You don't want them to include analytics. You don't want them to include an order by. You don't want them to be compound queries. There are certain structures that will stop views from being mergeable. And tuning your views to make them mergeable is a big and important topic. And that's something where the programmer, the developer, definitely can have a big impact on performance.
Thank you. And one more. What do you mean by a costed decision made during parse?
Oh, I sort of skipped over that, didn't I? The optimizer relies on statistics, which your DBA should be generating. And statistics about the data. Very simple statistics, such as how many rows are in each table, but also much more complex ones. Given the filters, the predicates in your query, what proportion of the table is actually going to be selected? Are we going to select 1/10 of 1% of the rows? Are we going to select 10% of the rows? And the statistics the DBA builds up allow the optimizer to work out and predict how much data is going to be involved. And that information is converted using cost-based optimizers' internal algorithms into an estimate for how long it will take to run the query using different join orders. If you join A to B to C, the query might take 10 seconds. If you join B to C to A, it might take 1 second. And the choice, the costed decision, is based on every operation is assigned what they call a cost, which is typically a combination of I/O activity and CPU activity. And it uses statistics to calculate those costs and thereby choose the optimum way to run the query.
Okay, thanks, John.
Moving on then. ANSI syntax. Right now, this was introduced in 9i. I was working for Oracle Corporation when 9i was released and when ANSI syntax first came in. I remember way back then, there were a fair few bugs with it. Some of them were pretty bad. But that was a long, long time ago. As far as I know, there are no bugs left. right? And you can now use ANSI syntax pretty much anywhere, There are still a couple of places. The only places I've noticed where you still can't use ANSI join syntax are in bitmap join indexes. And I found in some cases with materialized view rewrites, ANSI syntax doesn't always work too well. And maybe you have to put in a couple of hints and things sorted out. But generally speaking, ANSI syntax is not new. It's been around for decades. Right. Now, I'm one of these boring old men who thinks it's new, therefore it's bad. That is not the case, I strongly believe, with ANSI syntax. I nowadays believe that it is vastly superior to the Oracle native syntax. This is, of course, open to debate. The general idea is that with Oracle native syntax, we might have, for example, select star from emp dept, where emp.depthno equals dept.depthno, and dname equals sales, for example. Oops. emp.dept equals emp.depthno. What's wrong with that?
Syntax error, yes, okay.
Thank you. Okay. Those of you who spent any time with me will know that I am famous for making stupid mistakes like that. So, and that's your Oracle native syntax. Whereas the ANSI equivalent will be select from emp join dept using depthno, where dname equals sales. Well, and of course we get the same result set. That, by the way, two equivalence equals. Right. The equivalent, totally different syntax, guaranteed to deliver the same result set. Why do I prefer this latter syntax? To me, it's more understandable and less prone to error. What we've got is a join clause where we have the join filters, predicates, and a where clause where we have the filters. So you've got join predicates in a join clause, filter predicates in a where clause. And in my opinion, that's much easier to read, much easier to understand. But that is, of course, open to debate, very much so. And I'm never going to say that I'm always right, but I feel that the ANSI syntax is generally better. I'm prepared to debate that if anyone wishes.
I'll just add something to that, John, that if you use the Oracle native syntax, as many people do who have been working with Oracle for a long, long time, it's always better to join first and then filter and not make sort of a mixture of both. So at least you can see it better.
That's so true. Let me just give me a moment. Here we are. This is an example that should make you, Gary, cringe. And for everybody else, this will explain what he's talking about. This is from eBusiness Suite. And then if any of you work with the horror that is eBiz, you'll recognize what's going on here. So this is eBusiness. This is Oracle's own code. Create or replace force view apps.po negotiated sources v. And there are column names. Then we've got the select statement on which the view is based. So we're projecting all these columns. We're projecting these columns, all okay so far. And then we've got a from clause. And we've got about 20 tables here. Right, so a reasonable query so far. But then you look at the where clause. Remember, this is an eBusiness Suite view. Yeah, this is Oracle's own code. And think what Gary just said about separating your filter predicates from your join predicates. Look at this code here. Where? That's a filter. That's a filter. Then there's a join. There's another join. Then we're back to filters. More filters. And all of a sudden down here, a join. PH to PV. Another join. PV to HP. What do you think of this, Gary? Is this one of the worst bits of code you've ever seen? And it's impossible to work out what's going on. So if you do use Oracle native join syntax, please don't write your code like this with a horrible jumble of join filters, join predicates, filter predicates, then more join predicates. Yeah, looking at this, good hell, I just noticed this code is bad in so many ways, isn't it? Look at that. Totally unnecessary truncation. And that's going to suppress index usage. And there's no need to NVL it because you've already, well, never mind, that's off topic anyway. So if you're going to use native join syntax, don't write it like this. It makes the code so difficult to understand and terrifying to modify. My preference, ANSI syntax, but it's up to you. Okay, types of join. Well, these are the standard join types that we're normally working with. So what we've got here then is beginning with equi joins and non-equi joins. We'll just knock the house the way early on. Usually we use equi joins. In the case of an equi join, for example, select star from emp join dept, and I won't use the using clause. I'll make it absolutely clear on emp.depthsnow equals dept.depthsnow. That's an equi join. What do we mean by that? In the join clause, we've got an equality operator. What if we wanted to have, say, a non-equi join? A non-equi join. You don't see them so often, but you do get them. I'm just going to put that in brackets to make sure we don't get any confusion. I could join to another table. There is the table, for example, in again Scott schema. Select star from sal grade. The sal grade table. Oops. Describe. Don't be stupid, John. Select. That's better. Select. Start from sal grade, and depending on your salary, you're assigned to a certain grade. So if I take my little query here, select star from emp join dept on emp.depthsnow equals dept.depthsnow, I could expand that query to add in my next table, a non-equi join sal grade on sal between low sal and high sal, for example. That's a non-equi join. That's all it is. I'm just not using the equality operator. In this case, I'm using a between operator. And we should find that we've got grades in there now. So we now see that this person, Mr. Miller, whose salary is 1,300, is on grade 2, which is between those. So that's just an example of a non-equi join. We use something other than an equality operator. Equi joins are what are usually used in most requirements, so that's what I'm going to use from now on. So what do we have next? The inner join. Well, we all use inner joins all the time. I'm going to work on here I'm in the HR demonstration schema, which I'm going to use for a couple of other demonstrations here. I'll be skipping between Scott and HR demonstration schemas here. So for the equi join, well, what have we got in HR? Well, we've got a table called employees, keyed on employee ID, and a foreign key department ID, which joins us to a table of departments, keyed on department ID. Now, the inner join couldn't be simpler. Example. Select e.lastname, d.department name from employees, e join departments, d on. Right, well, I could have used the using clause instead. And there we go, we get back 106 rows. Right. Or if I wish, I can group my people into departments. A variation, select count, e.last name, d.department name for employees, e join departments d. On, there's the equi join, and then group by department name. And apparently this would seem to imply that there are 106 employees and there are 11 departments. And if I were to sum those up, that would come to 106. So on the face of it, 106 employees and 11 departments, but that isn't true. That isn't true at all. Let's see what an inner join actually does. Now, if you go to the internet and just Google SQL, if you just Google SQL joins and look at the images, most people like to represent joins as Venn diagrams. Right. I'm going to use this one. That's quite a nice one I found. So I downloaded earlier. So looking at that Venn diagram, you'll see that the inner join, you've got two row sources, and you want the rows where the key is common. So inner join, syntax there, select list, that should say column projection list, from table A, inner join table B, and there's the equi join syntax. So we want the intersection of the two rows. Right. But that isn't the full picture, because if you actually look at this, how many employees do I actually have? I don't have 106. I've got, they're actually 107. I don't have 11 departments. There are actually, oops, sorry, run this again. There are actually 27 departments. So my inner join has lost one employee, and it's lost 16 departments. To get the full picture, we need outer joins. Left outer join, right outer join, full outer join. So, left inclusive, select whatever from table A, left outer join table B, on, and there's your join condition. So I'll try a left inclusive. So here it is. So my statement was select e.last name, d.department name for employees, e left join departments D. That tells Oracle I want every row from employees, whether or not there's a matching department. And we get, therefore, 107 employees, I get 107 rows back. And there's the extra one, Mr. Grant, who is not in a department. Right. So to include him in the join, in the result set, Oracle has generated a null row in departments. Right. Or to get all the departments, and remember for all the departments, there are in fact 27 departments, whereas here I saw only 11. To get all the departments, I would do a right join, which would be select e.last name, d.department name for employees, right join departments D. And now I get 122 rows. That is the 106 employees that have a department, plus the 16 departments that have no employees. That will be the right outer join in this case. So it's the 106 from the inner join, 106 from the inner join, plus the 16 departments that have no employee. But it's still not the full picture, is it? The solution to see all staff and all departments is the full outer join inclusive. So coming back to this Venn diagram, left inclusive, all the employees, but missing some departments. Right inclusive, all the departments, but missing Mr. Grant, the employee without a department. full outer inclusive is the full data set. So when would you use a full outer inclusive? There could be any number of reasons. I was doing it just the other day. It was the application, the way the application had been designed. They had a table of live data, which had a few million rows, and a table of archive data, which had a few billion rows. I won't go into why the application had been designed that way, but it had been. So you had live data in one table, archive data in another table. Well, if you want a query that's going to show you the whole picture, you need a full outer inclusive. And there were many, many queries that needed rows from both the live data and stuff that's been archived. Basically, it was a bad design. So full outer inclusive as an example, that was not a bad one. Two data sets that you need to combine and get the, not the intersection, but the sum. So syntactically, full outer inclusive. Let's just try that here. Oops. So, and copy and paste. So my statement here is select e.lastname, d.department name from employees E, full join departments D, and then the join clause. And we get here the 106 rows from the inner join, plus Mr. Grant, who has no department, and at the end, the 16 departments that have no employees. So that's your full outer join.
John, this construct is not possible with the Oracle syntax.
It's pretty difficult. Yeah. You can sort of fake it. I did prepare an example, and since you mention it, I'll show you, and you can tell me what you think of it. I think this would be something similar. Select e.lastname, d.department name from employees E, departments D, where department ID equals department ID, and I've got the plus there. Union all, do it the other way around. Right. So what I've got here, but that's going to be wrong. That's going to be wrong, I think. But what that is, that's an outer join in one direction, and that's the outer join in the other direction. But if I run that, 229, I've got too many rows. And that's because the inner join has come through twice. Which makes it so difficult to get. We've got duplicates. I can try to get rid of the duplicates. I took that further. Instead of using, let's do it, instead of a union or, let's do a union. So there's the two outer joins. Let's union them together. 121. It's still not right. And that's because, unfortunately, there are some duplicate rows. It's a horrible bug. You might not realize it, but it's thrown up a horrible bug there. So even that bit of code, remember what that was? That was this. That's wrong too. It's discarding too many rows. These are horrible things to do. I did find a way that really worked. No, I think this was the technique I found that finally got it right. So if you really are, oh, there we go, 123 rows. That's the 107, the 106 in the inner join, plus Mr. Grant, plus the departments have no employees. So that statement is horrendous. Select e.lastname, d.department name for employees E, department D. So that's an outer join in one direction. Union all, but add the filter e.lastname is null. And that gives you a full outer join. So I think, Gary, you are correct to say you can't really do this with native syntax.
You can, but we see your point. We see your point.
It's a structure that's so prone to error. So prone to error. Thank you for that. Okay. Gary, can you just give me a quick break to get my throat back?
Sure. start, John. And we did have one question too, but I'll give you the quick break first. Everybody, thanks for joining us today. I think most of you have been with us before. You know, we're here for you. Consulting, training. We do it, DBA developer. Apex has been a biggie for us lately as well. You know, we can brag, but we're not like that. We do these to give you some good material knowledge, and if you need us, you know, come to us, and we're here. That's it. That's as far as the sales thing. John, let me ask you the one question. I should have asked you this before, and but when does where clause filter apply, before join or after join to dataset?
Typically, the where will be done as part of the select process early on before the join. Sometimes a where clause will be applied after the join if there were non-mergeable subqueries. So the where should come in as part of the select phase before the join. Okay. The syntactically, of course, it comes in afterwards, which I suppose is a bit odd. Okay, thank you for that. In that case then, let's finish this off then. So we looked at please.
Sorry about that. Could you use left outer join, union right inner join?
Left outer join, union right. You could try. I'm not going to sketch that out at the moment. Have to come back to you on that one.
Okay.
Sure,
and then the last comment from Chris. I guess the explain plan would show that.
If we come to execution plans, things are going to be hell on earth. And if we look at this, for example, I've got my 123 rows, and that's with the Oracle native syntax. So I set auto trace on explain. Let's see how it does it. Whee! Right. So my statement was cost is 11. Yeah, so what it's had to do is construct. That was using Oracle native syntax. Right, so it's come through with 123 rows, cost is 11. And there's one outer join, there's the other outer join. Right, this is just fancy work with indexes. So it's had to do exactly what I asked it to do. It's done one outer join, employees to departments, then the other outer join, the departments to employees. And it's applied the filter, which is chuck out the nulls. Whereas if we look at the equivalent for the ANSI join syntax, we did say that we weren't going to spend much time on tuning, but this is a lovely one to look at. Let's see what that says. So that's the ANSI join, the full join. So remember, it should be returning 123 rows, and it does. And it's half the price. We've hit each table only once. So, thank you for those. Let us revert to. So that was outer joins. So we looked at inner join, left inclusive, right inclusive, and full inclusive. Then we come to left exclusive, right exclusive. Now, these are what. So the left exclusive is all the rows in one row set, excluding those that are common to the other row set. Right. In effect, it's all the rows in the first set minus the intersection. And you can, if you want, write it as a compound query. You know, select star from A minus the inner join of A to B. So you could code it manually as a compound query. But of course, we don't want to. What we want to do is do it in one query, not as a compound query. So what this would be, select E.last name, D.department name for employees E, left join departments D, on e.department ID equals d.department ID, where department ID is null. So that will exclude these guys. Now, and if we look at that, we should then get only Mr. Grant. So we've got that one employee who does not have a department. Right. Or to go in the other direction, so this would be right join, the right exclusive. This is a way to get the departments that have no employees. Right. And that will be that one, the departments that have no matching employees. Now, it's very tempting to those brought up before ANSI to use alternative structures, such as this. Again, if you were not doing it with ANSI, how about this? Select department name from department D, but department ID not in. That would be a similar way of doing it. But it doesn't work, does it? In principle, this looks fine. I'm guessing the departments, that subquery there gets the department IDs of every employee. So I want the departments where there aren't any. And I've got no rows back. This is a classic bug. Gary, can you spot what it is?
It's as soon as it gets a null value in the select statement, it returns none.
Correct. This is a frightening sort of bug waiting to bite. It might work all through development and test, and then you go live and you get the wrong results. Of course, what it should be, the solution, is to make it an exists query, right? So what it should be is where it needs to be as a not exists query instead, something on departments D where not exists, and then we'll put a different subquery here, which would be something on these lines. Select X from employees E where E.department is, so a different query, and now I get
the
root exists.
Yes.
There we go. So bear that in mind. You can get the left exclusive or right exclusive using Oracle native syntax, but be careful, because it's so easy to make a mistake like that. And you might not find the error until a long way down the line, whereas that is the way it should be done. Okay, that was excluding. Then we've got a couple of oddities. Left, right, excluding. Okay, so Oracle calls this the anti-join. And you'll see anti-join in your execution plans before anyone asks. So the official terminology is right exclusive, left exclusive. Oracle terminology, it's an anti-join. Now, then we've got full auto exclusive, this one here. I came across this, oddly enough, just last week. One of our colleagues who's involved in the development of an application, I've not been involved with it other than very much on the fringe. It's something to do with handling some sports tournaments. And among other things, they have a table of teams and another table of competitors. And every competitor is meant to be in a team. And he came up with a perfect usage case for full auto exclusive. And what it was an exceptions report. They needed a report that would list every competitor who had not been assigned to a team, and also every team that had not been assigned any competitors. Perfect solution, full auto exclusive. This might be the team members that have no team, the competitors with no team. This might be the teams with no competitors. So full auto exclusive might sound like something quite obscure. It isn't. And that was a real world example, came up just last week. So the syntax, as we see, full auto exclusive, select whatever it is you're projecting from table A, full auto join table B, exclusive, on that where there are no, where you've got null values that have been generated. So if I run that in my example, I've got it here. Oops. I put in a coalesce here just to be clever. What I'm doing here is I'm selecting for employees full join departments D on equi join clause, and then the filter. And that gives me Mr. Grant, who has no department, and 16 departments that have no employees. So for my colleague Tyson's report, this was the exceptions report that listed everyone whose registration was basically incomplete in some way. So that was the left-right excluding, including in particular full auto exclusive. So let's run through the 7 common join types. But for the last 5 minutes, a couple more. Natural join, cross join. Okay, natural join. For example, select star from emp, natural join dept. Oops, emp. Seems to have worked. Gary, any comments? I think any halfway decent programmer is going to say that this is abysmal.
Well, I can say I wouldn't use it, and especially in the case of emp and dept, you're going to run into trouble because it's going to join what you think it should join, and it joins it joins on the name, so it could join to the wrong column.
Exactly. It works in the case of emp and dept, but that's purely luck. If I try it in the HR schema, for instance, select last name, department name from employees, natural join departments, where we know this should be an inner join returning 106 rows. Well, it doesn't, it returns 32 rows. And that's simply because the data is just not appropriate to it. As Gary said, it matches column names. So here it's worked, because if you look at emp and then you look at dept, there's only one common column, dept's no, and it's worked. I've got my 14 rows back. But if we look at the HR schema and we look at employees, and then we look at departments, yes, department ID is a common column, but unfortunately, so is manager ID. And that's why you should really never use natural join. Right. And finally, we've got the cross join, also known as a Cartesian product. Right. So, what do we find with the cross join? Well, if I select, I'll go to Scott again, and so that was select ename, dname from emp cross join dept, 56 rows. They've been multiplied together. Now that is 14 employees multiplied by 4 departments. So the cross join. Typically, or very often, it's a programming error. There are occasions where the CBO may choose to use it. I found a perfect example of the programming error. I've just got time to show this on a forum not so long ago. If you take a look at this example, right. So here we go. This is one of the better Oracle forums. And this chap says few years ago now. I'm trying to load data using this query. It's taking forever to get results. Right, and here's his query. So he's projecting these columns from these tables. Where? Oracle native syntax. And it's good syntax. He's got the join predicates followed by filter predicates. Right. So, W Moore, I wonder who he works for. So, but never mind that. And it's taking forever. I think lower down here, he posts the execution plan. Yeah, there's the, somewhere or other, there's the execution plan. Save. Right, so here's his execution plan for that query. Stretch that out a bit further. Right, well, the query is apparently, which he says, it's taking forever to get results. And that's because the query is going to return 28 trillion rows. Right, costed at 85 billion. But that 28 trillion rows is actually filtered down from 562 trillion. Right, so what's gone wrong? Merge join Cartesian. Right, he's got a Cartesian product in there. And this is where, if you come back to what's going on here, look at the row sources and count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. He's joining 12 tables. Then we come to his join filters. How many of them has he got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You can't join 12 tables with 10 predicates. Right. So it's a straightforward programming error. But that having been said, if you see Cartesian join in execution plan, it may actually be because the optimizer has chosen to do it. Now, if the optimizer is absolutely certain that one of the row sources will return only one row, then perhaps there's a filter, equality predicate on a primary key. If the optimizer knows that there's only one row coming back, it may choose to do a Cartesian join, because it can then be a very fast way to do it. But of course, you have to know your data perfectly. And that concludes us. So all sorts of joins. We've gone through a lot, inner, outer, full, exclusive. My preference is for ANSI syntax. I gave you that example of nulls distorting results. And that was my not in, my anti-join, using not in rather than exists. And of course, tuning. Well, one could go on forever about that.